So a few days ago, I received this doubt from one of my students, like how to solve these kind of numbers. Yeah, so this kind of numbers can be solved very easily with the concept of logarithm. And you can deal with more complicated numbers like this also. And you can play around with this idea also, which I will explain right here. But one thing I will tell you that you cannot solve these kind of numbers because here you have a negative base, and it's very difficult to comprehend what this expression could even mean. So negative bases will not be allowed, but negative powers will be allowed. There are other few trivial cases which may or may not be allowed in the base because of um, mathematical formality, but I am going to make it very simple. I will not go into the domain and range of all these kind of functions. I will just tell you that negative powers here in the base will not be allowed. Okay, so let's deal with this. To solve these kind of expressions, you need to understand the inverse relation between log and exponential. Just like you have addition and subtraction, right? Addition and subtraction are inverse of each other. So what does this mean? Suppose if I take 2 and if I add 5 here and if I subtract 5 here, you see these two operations have done the exact inverse of each other and we get back 2 again, right? Similarly, logarithm and exponential. Logarithm also has a base. Let's say logarithm, let's call that base b. So, and here you can put anything. So this is x. So this is logarithmic function of base b. And exponential also has a base b. So this is an exponential function. Here this base is b. So logarithm also has a base. Exponential function also has a base. And if we apply these two functions in whichever order, we don't get a change in output. Just like when we add something and subtract the same thing from a number. So to understand this, let's think about this expression. 2 to the power 4 is 16. I think everybody knows that. And this fact here can also be written, this is written in exponential way. We are using an exponential of base 2 and we are using 4 as a power and we get the answer 16. This can also be written like this. We can use the log of base 2 and we can say, we can, instead of 4, we can write 16 here and we will get the answer 4. What does log mean, by the way? Log to 16 is a number which when raised to the power of 2 gives you 16. So how can you transform this 2 into 16? What power will you use? This is the value of log to 16. Okay? You can feel the sense of inverse in this way of talking, how I'm talking about this. Okay? So let's see. So if we apply both these functions together on 16, if I take 16 and apply a log of base 2 and then I apply an exponential of base 2, I will get back 16. You can check it. So 2 log 2 16, and we already know that log 2 16 is 4. So 2 to the power 4 and this is 16, right? So you can go like, you can do this way, but even if you are not able to solve the log here, still you can understand that a log ab will be b, because you have taken b and you have applied logarithm of base a and then exponential of base a on b, and these are inverse relations and they will give you back b. Okay. Similarly, 10 to the power minus 2 is 0.01. We can write this fact in logarithmic terms as log 10 0.01, and that power which transforms 10 to 0.01 is minus 2. And if we apply both these functions together to 0.01, we take 0.01 and we apply a log of base 10 and then we apply an exponential of base 10 and we get back 0.01. You can verify it on your own. Okay, so you can say that a log a b is b. Similarly, you can do the reverse here. With this fact, you can play around. You can do the reverse here. You can, sorry, you can take 4 and raise and make an, you can use an exponential function of base 2 and then apply a logarithm of base 2, and you can verify that this will be 4. We are doing this time in the reverse order. We are applying the exponential first and then the logarithm, but both of them of the same base. And in that case, we will see that 4 will come out as 4 only, because log 2 to the power 4 will be 16, and we know that log 2 16 is 4. Okay, so similarly here also, you have taken minus 2 and you have applied an exponential function of base 10, and then you have applied a logarithmic function of base 10, and then you get minus 2 back. Okay, so this is another thing which you can say. So these formulas are valid for in their proper domains. I am not going to talk about domains. I just want to say that the bases should not be negative. Okay, so now to solve those expressions which you encounter in your examinations and you are worried how to solve them, you can solve it very easily. But for that, you will need the log table, and I don't want you to memorize the whole log table. I want to give you a very nice solution that if you know log 2 and log 3 in the base of 10, then you can solve all those kind of expressions. Let's first think about log 10 1. Log 10 1, what should be the power which transforms 10 to 1? And we know that 10 to the power 0 is 1. So log 10 1 will be 0. How about log 10 2? What should be the power of 10 such that the answer is 2? So this is a little bit tough, because we know 10 to the power 0 is 1, and we know that 10 to the power 1 is 10, and we know that if we keep on increasing the power, we will get bigger answers. So we know that exponential is kind of an increasing function. So if we want the answer between 1 and 10, if we want the answer to be 2. So what is that power? That power should be between 0 to 1, right? And do we know any other power of 10 between 0 to 1? I think we know one of it, like 10 to the power half, which is root 10. And we know that this is going to be more than 3, because root 9 is 3, right? So this will be 3.1, something like that. So we know that if we want the output to be 2, we can't use half, because 10 to the power half is around 3.1. We will have to use a number less than half. Half is basically 0.5, less than 0.5. So this value is going to be less than 0.5. Actually, it turns out to be 0.3010. And for two significant digits, I'm just going to go with 0.30. Okay. So this value I would like you to memorize to solve these kind of questions, which was asked in the first slide. Then log 10 3 also, log 10 3, you can also guess that this will also not be 0.5. This will be less than 0.5, because 10 to the power 0.5 is going to be 3.1. So it has to be a little bit lesser than 0.5. 10 to the power 0.48. So these are the two values I think you should keep in mind to solve the questions. Log 10 4. Okay, how to deal with log 10 4? It can be dealt with log 10 2 only. How to do this? Let's see, log 10 4. Okay, so log 10 4, you can say that this is log 10 times 2 into 2. Okay, and then now I'm going to break this thing up into log 10 2 plus log 10 2, and you will say why. So I will tell you why. This is nothing but law of exponents. So log 10, and I can write 2 as 10 to the power log 10 2. You can see that I am applying a logarithm and exponential of same base and 2 on 2. So I will get 2. 2 is equal to 10 log 10 2. Okay, and then another one, another 2. This 2 also we can write as 10 to the power log 10 2. What happens now? So we have 10 to the power something multiplied by 10 to the power something. And this I'm not going to prove. I think like this is the very famous law of exponents. And if I go into it, then this lecture will become more philosophical. So 10 to 10 to log 10 2 plus log 10 2, right? And this becomes log 10 to the power 2 times log 10 2. And now you see that you have taken 2 times log 10 2 and you have applied an exponent of base 10 and a log of base 10 on this, and they will cancel out basically, and you will get 2 times log 10 2. So this is what I was doing here without the proof, and this will be 0.30 and 0.60, right? Similarly, log 10 5 can also be dealt with 2. Log 10 5 will be log 10 by 2, and then again the law of exponent, you know, a to the power b divided by a to the power c will be a to the power b minus c. This same thing you apply here and you will get log 10 10 minus log 10 2. Then log 10 10 is of course 1 and log 10 2 is 0.30, so you will get 0.70. Log 10 6, you see that 6 is made up of 2 times 3, right? And then you can apply the law of exponents in logarithm, and you will get this. So you add basically these two values and you will get 7 8. Then the other values, you see log 10 7 is very difficult to deal with because it's a prime number. 7 is a prime number, so you can't break it up into two factors, so you will have to approximate it. Log 10 8 you can calculate using log 10 2. Try on your own if you have not done it before. Log 10 9 you can calculate using 3, log 10 3, yeah, because it's made up of 2 3s. 9 is 3 times 3, and log 10 10 of course is 1. So you can write all the values in this table except for this value, and this you can approximate that it will, if you know log 10 6 is 0.78, you know log 10 8 is 0.90. What is the number between 7 8 and 90? So you add these two and divide by 2. You're doing a very rough approximation. Let's see what it turns out to be. So 78 to 90, I think you have a difference of 0.12. So you take half of the difference and add it here, and this will be 0.84. Pretty interesting, but it was not exactly 0.84, because if we take more significant digits, then you would know that the logarithmic function is rising slower. Initially, you see from 1 to 2, the gap was 0.3. From 2 to 3, the gap has decreased to only 0.18. Here the gap was 0.30. Here the gap has again decreased to 0.12, right? And here the gap has decreased to 0.10. So you will know that this gap here from log 6 to log 7 will be greater than the gap between log 7 and log 8. But as it turns out to be here in 2 significant digits, that you can just take the average value. Interesting. Okay. So now how to solve this expression 1 by 8 to the power 0.6. So let's see. What we are going to do, we are going to use a base of 10, of course. We are going to use a base of 10 in the log or in the exponent. So how can we do that? The base now is 1.8 and we are troubled with this kind of a base. Leave alone the power, which is also very troubling, 0.6. But I focus on the base first and I will change the base to 10. How can I do that? So I can do this by, first of all, let's do a small simplification. This we can do that a to the, the reciprocal property, and then I will change the base. Now I will change the base to 10. So I will take this whole number and I will apply a log 10 and also an exponential of base 10 on it. You see? And I know that nothing will change, right? So I will do this, and then what I can do is I can use the law of exponent here. So log 10 8 to the power minus 0.6, okay? And this can be written as this power here will be multiplied to log 10(8). Why it can be done? This can also be proved using the law of exponents. This can also be done that way, but I'm not going to go into the proof right now, maybe in the next video. So this I can do here, and log 10(8) I know from here is 0.90. I will use this value here and then multiply. So what I'm doing here is like log 10(8). I'm not using log 10(8). I'm writing it as log 10(8) to be log 10 2 to the power 3 and 3 times log 10 2. So just to show you that I'm only using log 2 and log 3. So this 3 gets multiplied to minus 0.6 here. That becomes minus 1.8 and log 10 2. Okay, then we can use the value of log 10 2. So minus 1.8 into 0.30. You can multiply it and you will get minus 0.54. Now this is very interesting. Now here you have almost got the answer. You are very happily in the base of 10. Before you were in the base of 1 by 8. Now we are in the base of 10. But now from here we have to write a value which will be in scientific notation. This is okay, but we can also approximate it in the scientific notation. For that, what you have to do is, you see this power here? This power you can write as a sum of an integer and a fractional part. This sign should be of positive. So you take minus 0.54. You see that it's between minus 1 and 0. So the last integer was minus 1. So you can transform it as minus 1 plus 0.46. Okay. And then you can apply the law of exponents. This plus here. So if you multiply these two things, the powers are going to get added according to law of exponents. So you have this. So what is interesting about it, that you have got the other part of scientific notation, which is in the 10 to the power something, and this part is definitely going to be between 1 to 10, because this fractional part will be between 0 to 1. Because of that, your 10 to the power 0 is 1, 10 to the power 1 is 10. So this part is between 1 to 10, and we are in the scientific notation now. And this thing you can now approximate from here, right? 10 to the power 0.46. 10 to the power 0.30 is 2. 10 to the power 0.48 is 3. So 10 to the power 0.46 should be 2 point something, very close to 3, right? So 2.7 or 8 maybe, something like that. So I write 2.ab times 10 to the power minus 1. So basically, I'm sorry, I said 2 significant digits. We are getting only 1 significant digit, but this is enough for the competitive examinations, because you will, if you are not given the log table or nothing like that, then you can not, they are not expecting you to be more exact than this. So this is basically, this is 1 by 10. So you divide it and 0.2 AB, something like that. So let's check what the calculator says. And the calculator says that this is 0.28717, and we are close, 0.2. And we know that this A and B, this A would have been much greater than 5. So this is 0.28. Okay, let's try another one. 1 by 10 to the power 0.3. This is very nice because we are already in the base of 10. We just have to do this, use the reciprocal property. And then you have to break this power into an integer and a fractional part, and you would like to have a plus here. So you will have to go to the last integer. So minus 0.3 is between 0 and minus 1. You will have to break it down using minus 1. So when you do that, you get 10 to the power 0.7 plus 10 to the power minus 1. This part is between 1 to 10. You can approximate it. Oh, it turns out to be very close to 5. So you can say that this is 5 into 10 to the power minus 1, which is 0.5. Let's see what the calculator has to say about this. 0.501187. Very nice. Let's finish with an difficult example like this one, 0.002 to the power minus 5.9. So this base is very tricky. First of all, I would like to write it in terms of scientific notation, maybe. Yeah. So 2 into 10 to the power minus 3 and to the power minus 5.9, and then I'm going to change the base to 10. Okay, so now I change the base to 10, and I know that this will be multiplied to this whole part here, and this, the inside, this, the logarithmic part will be, again you can distribute the logarithm on multiplication, and you can add this, and then you know the value of log 10 2, you know the value of this also, right? So no matter what your base is, you can change it into scientific notation, and then you will only need these to know the log of this part, which will be between 1 and 10, and we know the values of log 1 till 10, so we can calculate this. So we, even with very tricky bases, we can solve. So what next? Log 10 2 will be 0.3. This whole thing will be minus 3, and then you solve a little bit, and then you come to 10 to the power 15.93. How do you break it down? You will go to the last integer of 15.93, which is 15, the integer just before 15.93, and you will break it down like this. Then you will apply the law of exponents, and then you will approximate 10 to the power 0.93. So that would be somewhere here, 8 point something, right? So 8 point something. Let's see what the calculator has to say about this. 8.39. Okay, thank you for watching. If you are more interested in exponents, you can always post your doubts in the comment section. I would love to answer them. If you are philosophically inclined about the fundamentals, the origin of these kind of functions also, I can also help. Just post a comment. Thank you for watching.